Okay. So welcome everybody. Today, I hope everything is okay. You can hear me and so on. If everything is okay, just give me a sign on Discord. Um, so let's resume our discussion about arithmetic devices and arithmetic algorithms used for designing these devices. These devices that can be that are actually used in processors and computer systems. So today, because last week we pretty much ended our analysis of multipliers and all those techniques designed to speed up the performance of multipliers. So so today we are going to open up a new chapter or subchapter actually. So it's 1.5 or 6, I don't know. I lost track of these. These are devices that perform division. Now, division is, as you may know and consider, it's a little bit harder and it's a little bit more complicated than addition or multiplication and all these other elementary arithmetic operations. So we are going to begin our discussion with simple facts. I mean, what is division? Division is something like this, right? You have a dividend, right? So when you perform division, you have dividend. You have to express the dividend as divisor times the quotient plus a remainder. And of course, you start with a dividend and a divisor. The thing is here that you want to find who are, so these are actually the inputs, right? And the outputs are the quotient and the remainder. So these are simple things, and you know this from elementary school, how to perform this in decimal, and I'll perform a quick reminder for you to this end. So for instance, I don't know, I take 121 and I try to divide it by, I don't know, 9. Okay, so it's 1, 31. You know how it works, so right, it's something like this. Okay, this is the dividend This is the divisor, 9. This is the quotient, and of course this is the remainder. So this is how it works in decimal. In binary, if you think about it, is quite similar, but the problem here, I mean, it's not such a big problem, is that you only have 2 digits, namely 0 and 1. So the outcome because as you can see here, you are forming the quotient digit by digit, right? First, you find that the first digit, the most significant one, decimal digit, right, is 1, and the second decimal digit is 3. So you construct the quotient digit by digit, right? And it's the same thing here in binary. The only thing is that you only have 2 digits, right? So instead of 10, you have 2. So this pretty much simplifies things a little bit, but you will see that they will become more complicated in other respects. So let's do it in decimal and in binary and see how it works. So 121, let's put it in binary. So it's 64, right? So I have 121 minus 64, so this is 7, 5, right? And 32, so it's 5, 25, 16, right? So it's 9, so 64, 32, 16, and then 9, right? This is 121. And 64, sorry, 9, sorry, is in binary is this. Now, let's make the division. So I have to do this. Now, the first thing is to compare, right, this quantity, which is the divisor, against quantity consisting of the same, right, starting from the most significant bit, the same number of bits, right, 4 bits. Now, obviously here the quotient digit is 1 because these 4 bits are bigger, the quantity represented by, or the value represented by these 4 bits, which is 15, it's obviously bigger than 9. So it's 1. So we subtract. And we have 1, so sorry, 0, 1, 1, and 0, right? And then we take this 0, okay. So again, we compare it against this quantity, and obviously it's a 1, so we subtract, and we got 1, we got 1, 0, and 0, right? So we take this 0, and obviously this guy, the divisor, is bigger than this quantity, so it's a 0. then we take this guy, which is a 1, and of course if we look at this quantity is bigger than this one, so it's a 1, so we subtract and right, we have this result. So, and this is a correct result. Why? Because this guy is obviously 13 in decimal, and this guy, the remainder, is obviously 4. So you see the same result. All right, so this is how it works in binary. Now, the problem here is that you see these comparisons for me as a human and for you as well. I mean, we are human, and we just take a look at these quantities and we see who is bigger than if we are taking a look at these 4 bits and these 4 bits, it's obviously that these 4 bits, the value represented by these 4 bits is bigger than the value represented by these 4 bits. But for the computer, it's not so obvious, right? And we must do something to perform such an operation. And how is this possible? Well, simply by subtracting these 4 bits from these 4 bits, and if the result is positive, then okay, the quotient digit is 1. And conversely, if this quantity, the divisor is bigger than these 4 bits, then the quotient digit is 0. But if it's bigger and you already did a trial subtraction only to see if it's bigger or not, if the quotient digit is 0, you will have to restore that quantity, right? To put it back here, for instance, here, right? I didn't perform the trial subtraction because with the trial subtraction I would have obtained a negative value, and then I would have been forced to put it back. So I didn't. So you know, that's how it works. Now I'm going to show you the entire what we will call as 1.6.1, the restoring division. Okay, now to present you this algorithm and how it works on you know, on an example, simple example, on 8 bits, I'll do the following example. So I'm going to divide 5,771 by 135. So this works like this. So it's the first quotient digit is 2. Sorry, it's 4. So it's 0. It's 2, 12, 14, 1, 5. Right? So it's 7. That's 3. Right? And then it's 2. So that's 270. And the remainder would be 101. Right, so these are the results that we should get, 42 and 101. Right, so okay. Now prior to going to, you know, okay, let's finish this. So first I'm going to put in this number into binary, this is in decimal, right? This number. So I'm going to put it in binary, and of course we have these quantities, right? Now this is the biggest one that is still smaller than this number. So, right? That's 5, 7, 6, and 1. The next one, 2048, is with a 0. Then there's 1024. Yep. So it's 1, it's 5, and it's 6. And then 521. Sorry, I messed up this. 512, obviously. I don't know what I was thinking about. So it's 9, it's 3, and it's 1. So, yeah. 256, no. 128, yes. So it's 1, and it's 1, and that's it. So there's no 64, no 32, no 16, and we are left with 11. Okay, so this is the binary representation of our divisor. Yeah, so okay, and the dividend, this is the dividend, and the divisor is 135. And this guy is okay, so 128. Right, so it's 7, and that's it. Right, so it's 7. 128, 64, no. 32, no. 16, no. And then 7. Right, so this is our divisor. Now, good. Okay, prior to doing this example, we have to discuss about something, namely the number of bits required. Obviously, when you are thinking about a division, you are representing divisions like an inverse multiplying operation. So you have, we made multiplications such as, 8 bits, an 8-bit operand 1, times an 8-bit operand 2, and you got a 16-bit product. Now, what I'm going to use this space here, right? But this should go here. What would be what would be the case for the division? Now, if you think about it, okay, you may want to take 16-bit dividend, right, and divide it with an 8-bit divisor. But the problem is this: the divisor can be any value. What about the case when the divisor is 1, right? If this value is 1, what would happen? Now, obviously, the quotient would be equal with the dividend, right? So then the quotient would be on 16 bits. And I don't want this, okay? I don't want this because I want both my divisor and my quotient to be on 8 bits, right? I want this guy to be on 8 bits, and I want this guy to be on 8 bits also. So what can I do? Well, the first thing that I can do is to force the quotient to start with the 1. The divisor, right? So it is the case here, right? This divisor starts with the 1, right? It doesn't start with a 0. Now, this is also okay, but when it starts with a 1, then what is the biggest quotient that can be? Well, the biggest quotient that can be is, well, if you take the 8-bit example, right? So you have 16 bits like this, only once, and you divide it by the smallest divisor that can be, so which on 8 bits, which is this guy, right? And to do this, okay, you'll compare this guy with 8 bits from here, right? So it's, I guess I'm going to use another. Let's save this. I named this file from CL division code div, but right now I'm realizing that this name is dangerously close to COVID. So yeah, yeah. So you see, what I'm trying to show you is this. So I'm having 16. Let's take this example with, it's simpler. I want to keep it simple. So without losing generality, and we are going to move from the 8-bit example to the 4-bit examples, right? So the equivalent would be that the dividend, will be on 8-bit, right? The divisor would be on 4 bits times the quotient, and I want this guy to be on 4 bits as well, plus the remainder. So this is a times, right? Times, and this is a plus. Okay. Also on 4 bits. Now the problem is that the biggest dividend that can be, which is on 8 bits, is this guy. Right? I want to, you know, divide it by this guy. Now the problem is that, and it's the same thing for the 16 bits, the 32 bits, is the same thing, because you have the biggest dividend that can be is only ones, and the smallest divisor that can be, which starts with a 1 on the most significant position, is this guy, 1 and then only 0. So obviously the first quotient is 1, so the first quotient digit is 1, so you will have only guys like this. So the second is, is this one, right? So it's and then the third one is this. So you got this, and the fourth one is this. And there's a fifth one over here. So surprise, surprise, right? This is the remainder, right? And this is the quotient. So in this situation, you would need 4 or 8 or 16 bits plus 1 for the quotient. Why? Because in this case, you'll have to make this comparison, so it's 1, and then you'll have to make the number of comparisons which is equal with the number of bits in the second half of the dividend, which is equal with the number of bits in the quotient and the divisor. So it's 5. So what can you do to avert this, right? What can you do? Well, one thing is, is to limit the number of bits in the dividend to 7. And in this case, indeed, right, you have limited, correctly the number of bits for the divisor and the quotient. Why? Because when you have only 7 bits, the biggest dividend that can be is this guy, right, on 7 bits. And the first quotient is made by, quotient digit is made by making a comparison with these 4 guys, and then you have other 3 comparisons. So this is comparison 1, and then is 2 and 3 and 4, which means 4 quotient digits, right? So that's why in these divisions, the divisor is on 2n minus 1 bits. The dividend, the divisor is on n bits. The quotient is on n bits, and the remainder is also on n bits. Okay, that's how it works. Now, I'll show you how to make this work by using 4 registers and of course is amenable to those structures, those Hayes platform structures, you know, with A, Q, and M registers, such that in registers A and Q you hold initially the divisor, and then the divisor is hold in register M, and eventually in register A you will have the remainder and the quotient in register Q. So I'm going to show you how this is done. Code div 2 here. So for the numbers that I showed you, those 5,771 divided by 135. So I'm going to draw come on. Something like this. Come on. Okay. So I have a counter. And then I said register A. When I'm using registers and operands on 8 bits, so n is 8, which means the divisor will be on 15 bits, right? But that number is okay. It can be represented on 15 bits, so no problem whatsoever. So this is register A, and this is register Q, and this is register M. First, the count is 0, and then I'll have the number. It's on 15 bits again, and that's because this bit, which I'm going to underline here, this bit is used, and this binary position is used to hold the first quotient digit that is to be decided. And then I'll put the bits of my number, my digital representation, which is here. Okay, it's here. Okay, so it's 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, and then 0, 1, 0, 0. Okay, so as I the divisor is 135, which is this guy. So I'm going to trial subtract it to see if what is the quotient right now is 0, it's 1. So I'll get 0, 1, and 1, and 0, and 0, and 1, and 0, and 1. So it's a negative quantity here. And because it's a negative quantity, it means that first I'm going to, well, the quotient digit is 0 for once. And the second thing is that I'll have to restore that value. So I'll add it again because I altered this value only to find that it doesn't fit over there. So I'm going to restore it, and it's 1, it's 0, it's 1, it's 1, it's 0, it's 1, it's 0, and 0. Okay, so this is the value restored. On the other hand, I know because of this guy over here that, you know, the value over here will be 0. Well, it was 0, but it remained as such. And then I'm going to shift it to the left. Why? Because the partial remainder that you saw in my paper and pencil examples, I'll have to put this bit also to take it into consideration. So I'm going to shift everything to the left this time, right? Okay. And then see if it works. Yeah. Yeah, but we're going to the next step. So again, we are trial subtracting. So it's 1, it's 1, it's 0 and 0, 1, 0, 1, and 1. Now, I didn't ask you, but I assumed, and I also assumed that I'm correct here, and I'm right, that you already know how to subtract in binary. So I'm not going to come back to this. So again, it's negative. So I'm going to restore. So it's 0 and 1 and 0 and 1 and 1 and 0 and 1 and 0. So it's restored, right? But this means that, you know, I have this in as the contents of register Q, and because of this value, of course, this guy would be 0. And then I'll shift it to the left. Again, I'm doing the same thing, the same routine. I'm trial subtracting. So it's 1, it's 0, it's 1, it's 1, and 0, and 1, and 0, and 0. Okay. So this guy is 0, and it means two things. First, it fits, right? The divisor fits. So I'm not required to restore it. And on the other thing is that the quotient digit right now is 1. So I have this as the contents of register Q. And this guy would be a 1. Why? Because, oh my god, of this 0. And then I'll shift everything to the left. And move to the next step. Again, I'll trial subtract. The result is 1, 1, 0, 0, 1, 0, 1, and 1. So it's negative, so I'll have to restore. And the result would be, after restoration, 0, 1, 0, 1, 1, 0, 1, and 0. And here I'll have now, because of this guy and because it's a 1, the value over here will remain 0, right, like here, and then I'll make a shift. Okay, like this, and I'm moving forward. Like this. Here I'm going to, let's extend this. Okay, so we made some more room. 1, 0, 0, and that's again trial subtraction. We subtract 1, 0, 0, 0, 0, 1, 1, 1, and get a 0. Yeah, 0, 1, yeah, 1, 0, 1, 0, and 0. And yeah, this is a 0, so it's positive, so the quotient digit in this step would be 1. So it's 1, and then shift. Sorry. So it's 1, 1, 0, 1, and 0 here. Okay. 1, 0, 1. Again, we trial subtract. 1, 0, 0, 0, 0, 1, 1, 1. We get 1, 0, 0, and 0. 1, 0, 1, and 1. So yeah, I don't know if this is correct. So I guess there's a mistake here. Let me find it somewhere here. So 1, 1, 0, 1, 0, 1 minus this quantity and this. This would be 0. So it's 0. Well, yeah. So here I have 0. Here I have 1. Yeah. 1. Right? 1, 1, 0, and so on. Right? So obviously here I'll have a 1 after the shift. And of course, when we subtract here, we'll have 1, 1, 0, and then 1. So it's 1, it's 0, and then it will be a 1, 1, and it's 0, 1, 1, 0, sorry, 1 and 1. Okay, so yeah, right now it is correct. Yeah, it is correct. Now, this means that I have to restore it. Which means that I have 0, 0, 1, 1, 1, 0, 1, and 0. And that is okay. It also means that the current quotient digit, because this guy's 1 will be 0, and then we shift. No. Okay. Let's see how it works. Now, unfortunately, I don't have enough space, so I'm going to because you see, M is the same thing in all these places, so I'm going to erase to make some room. Obviously, I'm going to erase now from here. Like this. You don't have to erase it yourselves when you make the table. I'm doing it only to gain some space, right? Because I don't have the space here to do everything. But normally it should continue. Obviously, I didn't write the contents again and again because it's the same contents, right? So that's why. Yeah, so it's like this. I'm going to simply, and also I'm not going to put register M in this continuation of the table, because you know why? Because it's the same value over there, so it doesn't add new information to what we already knew. Right, so now this should be right step 110, and you know what's above. Above is 101, and the values I'm going to write them because it's of great help to me. 1011, 1001, and this guy is 1001, 0, 1, 0, and 0. Now, I'll make a trial subtraction, obviously. Of the divisor, and it's 0 and it's 1. It's 0 and it's 0 and it's 1, 1 and 0 and 0. Again, a 0, which means that, you know, the quotient would be 1 here, and restoring is not required. And then we make the final step. So we trial subtract. So it's 0, it's 1, it's 1, 1, 1, 0, 1, and 1. Now, this means two things. The first thing is that I'll have to restore, right? Because this guy is 1, so I'll have to restore it. But at the same time, the quotient digit is 0, so it's 1, 0, 0, 0, 0, 1, 1, 1. So it will be 1 and 0 and 1 and 0 and 0 and 1 and 1 and 0. So it's restored. At the same time, I said that the quotient digit, the current quotient digit would be 0. Okay. And there's no more shift. So in the last step, we do not perform another shift. And that's it. Right? So let's verify that it's correct. Right, so here is register A, and here we have register Q. First, the quotient. So this is 10 plus 32, that's 42, right, in decimal, which is the quotient. And the remainder is 5 plus, this is 5, no 8, no 16, but I have 32 and I have 64. Is 9 plus 2, that's 11, and it's 1, so it's 10, 101 in that decimal, which is the remainder. And this is what we actually expected, right? So, okay, so we expected these values for the quotient as well as for the remainder. So it works, right? But it works, it renders the correct results, but here we have, so at this point I have two observations. The first one is that for division, the 2's complement representation would not work. I mean, it's of no use. There are no algorithms, as far as I know, and as far as everybody working in this field knows, to divide it according to some algorithm. So, on the other hand, establishing the signs of the quotient and so on, it's pretty simple when you perform divisions, because when you have the same signs, if the divisor and the dividend and the divisor have positive signs, so they are positive, both the quotient and the remainder are positive. When the divisor is negative and the dividend is negative and the divisor is also negative, the quotient will be positive and the remainder will be negative, and so on and so forth. So from the signs of the operands, you will see the signs of, you can separately compute the signs of both the quotient and the remainder. So these algorithms work with unsigned integers. Okay. Yeah, that's one observation. The other observation is that it's performance related. Now, remember our discussion when we talked about multipliers, right? So we analyzed this performance in terms of arithmetic operations that are performed in one step of the algorithm. And our entire effort in optimizing this performance was to reduce, on one hand, the number of arithmetic operations, and then with a hierarchics technique, the number of iterations altogether. So, but first, let's talk about the number of arithmetic operations, okay? Because that was the discussion when we analyzed modified Booth with Booth and so on. Let's see the situation here. So for multipliers, we're very we didn't like the fact that there are steps in which we do arithmetic operations, and we wanted to maximize the steps in which we do not do arithmetic operations and we do only shifts. Now, let's analyze this algorithm. This algorithm looks very bad from this in this respect, right? Because we are performing at least one arithmetic operation in each iteration, right? So we have eight steps, eight iterations, and 8 operations just for trial subtractions, right? Because we do the trial subtraction in each step. And then in some steps we are making we restore the values when the quotient digit is 0. In this example, in the example that we have, how many restorations do we make? So it's 1 here, 2 here, 3 and 4. 4 and 5. So it's 5 ops for arithmetic operations for restoring. That means a total of 13 operations, arithmetic operations for 8 steps. That's huge. So obviously we are not okay with these figures, and we are not okay with this non-restoring algorithm. So the first optimization of this algorithm was to, make this observation that we are always making this trial subtraction. So why not, considering this partial remainder that we are building step by step in register A with a deficit of m, a deficit of the divisor. So you are not holding here the normal quantity. You are holding here the normal quantity minus m every time. Okay? Because when you do this, in the next step, okay, if you have to restore it, in the next step, what would you do? You just add m, because when you shift it, you are making it minus 2m. Whatever is on there, minus 2m, because when you shift to the right, to the left, what you do is to actually multiply that partial remainder with 2, right? Shifting to the left means times 2. So it's times 2, but it's that quantity is on deficit of m. So it's the partial remainder minus m. So when you shift it, it's the partial remainder times 2 minus 2m, right? But that should be restored. Well, you restore only m. Why? Because it should be, normally it should be 2 times the partial remainder minus m, right? Because it has to be on a deficit of m. So you don't need to do the restoration all of the time. What you need to do is that when you encounter a 0, you subtract, right? Every time the partial remainder is positive, you subtract, and every time the partial remainder is negative, you add, and that's it. Okay, and that is called what we call the non-restoring division. I'll save this as CODiv3. And we are starting our discussion about 162 non-restoring division. Right? So what we did in our restoring division was this. Okay, we took, let's say in step Ri minus 1, we construct this Ri minus 1 partial remainder, which is held in register A, right? So we compute this, so the contents of register A contains in step I minus 1 this partial remainder. In the next step, so Ri was 2Ri minus 1, right? And then we trial subtract m, right? So that is the correct partial remainder. Now, if Ri minus 1 is not Ri minus 1, but is Ri minus 1 minus m, right? So in deficit of m, it means that Ri is 2Ri minus 1 minus 2m, right? Because it's 2 times this guy, because we shifted to the left. And to get the correct result here, the only thing that we need to do is to simply, if Qi is 1, so I have to restore it, then I'll do Ri plus m, which means 2Ri minus 1 minus m, which is the correct result here. But if Qi is 0, then I'll make a subtraction. I'll make Ri minus m. Why? Because there's nothing to add here. There's nothing to restore. Okay? So this is the non-restoring algorithm. Now I'll make the same algorithm here. I'll save this. Okay. And I'll make this because maybe this way is too abstract and too, hard to understand. So I'll do something else. I'll take the same example, the same two numbers that I performed, that I used to perform the restoring algorithm, and the first thing is that I need a bit that would tell me the sign of the result. So this will be the sign bit, and then the accumulator, the Q register, and of course the M register. Good. So I'll have here the counter. Count. I don't know. S, A, Q, and M. These are 8-bit, 8-bit, 8-bit registers. 1-bit, 3-bit. First S is 0, and I'm taking the same numbers. Again, this bit, which does not pertain to the dividend, is just there to hold. It's a binary position reserved for holding the first bit of the quotient. Okay, so because the sign is 0 and it's initially 0, I'll make the trial subtraction, the first subtraction. So I'm putting from the very first step, I'm putting minus M. So I'm making a deficit of M, a deficit of the divisor. So I'm subtracting. So it's 0. It's 0. It's 1. And it's 0. And it's 1 and 0 and 0 and 1 and 1. Okay. Now this guy is 1. So it means that this guy remains 0, right? So this 1 determines a 0 here. And then we shift. And the shift chain, shifting to the left, consists of register Q concatenated with A and concatenated with S. So that's what we get, and move to the next step. Now, as I said in my brief description of the concept behind this algorithm, if this is negative, then I'll add M, the divisor. it's 1 and 1 and 1 and 1 and 1 and 1 and 0, no, something is amiss here. So it's and something is not good. So it's 1 0. I guess this div is not okay. Yeah, something is mistaken here. So it's 0 and here is 1, right? Is 1. Yeah. Yeah, because here it's 0 and here we have 1. Okay, it's 1 and 0. So it's 1 0 and just a second, because there's another mistake over here. So yeah, and it's 1 and 0. Oh my God. Yeah, now I know what the mistake is. So yeah, I put the wrong divisor. This is our divisor. Yeah, that's why. That's why. And yeah, so it's 1 0 1 0. So this is 0 and this would be 1. Okay, that's correct. And then after shifting, yeah, 0 and 0, and it will be 1 here, 0 and 0, 0 1, 0 and 1. That's correct. Now this guy is also incorrect because I took the wrong divisor. So it's 1 and 1 and 0. So it's 1 and 1 and 0 and 0 and 1 and 0 and 1 1 1 1 and 1. Yeah. So it's 1 1 1 0 1 0 0 1 1. Yeah, that's correct. Now this guy is 1, right? The sign is 1, which means this bit is 0, obviously, and of course we shift, right? So, oh my God, 0 0 0 1 1 0 1 0 0 1 1 0 0 1 0 1 and 1. Okay. Next step. The sign is 1, so we add. So it's 1 and 0 and 1 and 1 and 0 and 1 and 0 and 0 and 0. Now we have a 0, which means that the last bit will be put on 1, right, because this guy is 0, and then we shift. Next step. Because this guy is 0, I'll subtract. The sign is 0, so I'll subtract. So it's 1, it's 1, 0, 0, 1, 0, 1, 1, and 1. Now, because this guy is 1, damn it, I copied the wrong information. So it's 1, 0, 1, 1, 0, 0, 1, and this is 0 because of this bit, and then we shift. Okay, because this is 1, we add. And we get 0, 1, 1, 1, 0, 1, 0, 0, and 0. Okay. And because this guy was a 0, the least significant bit is put on 1. I don't know why I wrote a 0 over there, because it's obviously a 1. And then we shift. Next step. Okay, again, because this is 0, I'll subtract. And the result is 1 and 0 and 1 and 0 and 1 and 0 and 1 and 1 and 1, because this guy is 1 here, yeah, I'll have a 0 here. And then shift. Okay, move to the next step. All right. This is negative, so we add. So we get 0 and 1 and 0 and 0 and 1 and 1 and 0 and 0 and 0. Therefore, the last bit would be 1 because of this 0, obviously. Okay, and then we shift 0, 1, 0, 1, 0, 1, 0, and 0, 1, 0, 1, 0, 0, 1, 1, 0, and 0. And we move to the next step. Okay, let's extend our table a little bit. Okay, so in the last step, this is positive, so we subtract. Therefore, we get 0 and 1 and 1 and 1, 1, 0, 1, 1, and 1. And because of this, because of this 1 over here, which means negative, this bit over here will be 0. We do not perform the shift. We saw that and we know that from the non-restoring, from the restoring division. But we have a problem here. So we ended with a deficit of m, and that's what happens all the time when the last digit of the quotient is 0. So when the quotient ends up being even, in such situations, it means that the remainder is negative, which is not correct. And it is negative. Why? Because we always have this deficit of m in our partial remainders. So we are forced in such situations. Remember that this step is not performed all the time. Okay? It's only performed when you end up in the last step with a negative quantity here. With this, actually with this s bit being 1 here. So in such situations, you are making a correction step, which consists of adding back, restoring that m deficit. So it's 1, 0, 0, 0, 0, 1, 1, 1. We add the divisor again. So it's 1 and it's 0. And it's 1 and it's 0 and it's 0 and 1 and 1 and 0 and 0. Okay, so yeah, so this is our result. Now let's see if these results are correct. The first one is obviously correct, because it's 10 plus 32, so it's 42. That's the quotient in decimal. This is the quotient, and this is the correct result. And the remainder is, again, we have here 5 plus, this is not 16, this is 32 and 64, and this is 11, right? 1, that's 10, so it's 101, and this is the correct result in decimal. This is the remainder. Now, let's get back to our discussion about performance, because let's see the performance here. So we are only making one, if you are taking a look back at this table, we only make an arithmetic operation per iteration, which means 8 operations plus, well, sometimes we have to do it, such as in this case. Sometimes if this bit would have been 0, then there's no correction step. But here we had a 1, so we were forced to perform these correction steps. So in our situation, it means 9 operations. Okay, so 9 instead of 13. Okay, we'll stop here for today with this thought that optimizations are still, this is code div 5. That optimizations are still possible, more optimizations, because we want more than this. We want an observation made by 3 guys, Sweeney, Robertson, and Thatcher, which means the SRT algorithm exploits that observation that sometimes you can simply make a no op in one iteration, only a shift. So there are possibilities when we are discussing about the non-restoring division. There are steps and situations where those steps can consist only of shifts, no arithmetic operations whatsoever. So that case, we will discuss that case and this algorithm, the SRT algorithm, next week, and then, okay, further discuss the fact that SRT is amenable to higher radix and other speed up techniques. So until then, I just want to, because I stopped and we stopped right now our discussion, but I want to maybe I'll put all these drawings on Discord, and I'll move to Discord and open a voice channel such that you can address questions, and I'll answer them. Okay. So I'll end my talk here on YouTube and my channel on YouTube. And we'll hear each other on Discord. Okay, thank you very much for being here and attending this presentation. Okay.